This Grand Challenge workshop is the high-latitude geospace system. Obviously not a new topic at all to the CEDAR community, but it turns out we are deploying an increasing number of sensors, heterogeneous sensors in a distributed form into the high-latitude system. And this includes not only ground, but space-based sensors. We have EPOP and SWARM. We have the RISER-N and the RISER-C facilities. So it's time to take another close look at Earth's open magnetic field line region. And so we proposed a Grand Challenge workshop to try and explore some of these notions. And so we're delighted this morning to have a tutorial speaker to try and help us orient our thinking a little bit in this direction. When the conveners of this session, when we started thinking about who has done the broadest spectrum of work in this area and who might be able to catalyze some thinking about open problems, Dr. Herb Carlson from Utah State immediately came to mind. And so I don't want to spend a lot of time into the session. I want to give him the floor. And so the tutorial this morning is going to be Challenges in High-Latitude Geospace Science, and it's going to be presented by Dr. Herb Carlson. So, thanks.
Well, it's a great pleasure to be here and talking with you folks, and it's also very exciting when you are getting into the area of advancing from climatology and characterization to trying to be able to talk about weather and prediction. It's a very different game that we're getting into. It is a new challenge, new thinking, new sensors, new synthesis, new modeling philosophy. I really mean it when I say you are getting in on the ground floor of a whole new wave of progress in a field that's been around a while, but this is really an exciting turning point. I'm going to start with a bit of characterization and some of the things that we know and we are pretty sure we do know, and then get into some of the challenges that we know lie ahead and why we're quite bullish about we're now getting ready to take it on. In terms of the high-latitude polar regions, You've heard many times that the solar wind input to the solar wind magnetosphere, ionosphere-thermosphere coupled system is where it starts, and the ionosphere-thermosphere response can be viewed in this regard, that you have the energy pouring in at the high latitudes, creating neutral pressure bulges that are opposing the subsolar pressure in the thermosphere. You have impulses, so you have gravity waves. It's really a global response, but I'm going to be focusing mostly on the high latitude part of that response. There are two states for the IMF North and the IMF South. This is the way the world looks for the southward IMF case. For the northward interplanetary magnetic field case, you've got a quite different situation. And in terms of, in contrast to a well worked over perception of how the topology of the magnetic field lines look for the southward case, we still are in pretty difficult territory to understand what's going on for the northward IMF case. But it is clear that we have two distinctly different states, one for the north, one for the southward IMF, one strongly coupled solar wind, one much more complicated coupling by the neutral wind. Now I'd like you to look on the left side of this. It's a cartoon that we did about 20 years ago just to try to orient our thinking. The sun is on the top, noon is on the top. We're looking at the plasma coming into a source region. The sun is up here. We're looking at entry of plasma going across the polar cap, coming out and exiting and going in either direction, and that plasma that exits can come around again. Now, this was a cartoon based on a scattering of ground-based sensors. Now, this looks pretty much the same, except this is a paper that appeared in Science last year, because it is actually a paper based on tracking real patches and tracking real measurements of electron densities. So what the authors did was to gather data from a large number of total electron content sensors, and what they've done is to put a black circle around here where the plasma is entering. The red stuff is a high density plasma. The sun is up here, it's dark down here, and the flow is, patches are entering here. They're going across the polar cap here. They're exiting the polar cap here. Some are going around that way, some are going around this way. And then here in the return flow, you've got some red spots, which actual real life, honest to goodness data over the course of about 3 hours. They tracked these guys going across, coming out, and coming back here. Now, that's raises a question, can you come back? You've got this ionization down here, what's conventionally called a blob, but do you have that high density plasma re-entering the polar cap? Well, in fact, here is a case where the so-called blob, less Kenver, did get in for a second time. This hook down here is that continuous electron density that came out from the midnight sector. It's now back around in noon. Now we've put the sun down on the bottom instead of the top, and we have this being segmented into different pieces. And in terms of, is it a continuous or a segmented entry? Up here are two different look angles from an incoherent scatter radar. These spaces between these red blobs are showing that it is being segmented. And down here, what you're looking at, you can see alternate red and blue. That's about all you can see from the audience. But the point of this measurement is you're looking at velocity vectors, and you are getting spurts of high velocity flow. And when you get spurts of the high velocity flow, that coincides with when you get segmentation to separate these high density plasmas. So the short answer is yes, plasma that starts out from the sun on the noon side, crosses the polar cap, exits on the midnight side, goes into return flow, has a second chance at doing it again. Most of the plasma that we see in the polar cap is not like that. I wanted to show not only the incoherent scatter radar measurements, which give you densities, temperatures, velocity vectors, but also what I'll choose to call images from Cutlass covering the same area. And here, what you can see from the audience as you're looking from left to right as time is progressing and then from top to bottom, you could see that the red areas are progressing first towards the west. So if you follow down any column, there's a westward progression of that red high density area, high echo area. And also it starts initially just going to the west, and then eventually it's working its way poleward, going into the polar cap. Now, if all that you had were the Cutlass data, you know that you're getting echoes. You're not entirely sure what the echoes may be from, but by the time you have combined it with these other measurements giving you the real temperatures, densities, velocities, there's no question, but now Cutlass is imaging these segmented pieces of electron density entering the polar cap. So that's, and then I've outlined in red here, again, the sun is up here, and this is the noon part of the circulation, and this is the general circulation pattern for a northward IMF circulation cell. This is for those of you who've been in the field for a while, a very well-known figure from John Foster. This red is the high electron density plasma. The sun again is at the top, and this is the high electron density plasma entering the polar cap, working its way across, following the lines of equipotential. Now, if you were a ball player, you'd be told, keep your eye on the ball. If you were a politician, you'd be told, follow the money. If you're in this game, follow the equipotentials. So this plasma is just following the equipotentials across. So there's no question but that high-density plasma follows the equipotentials into the polar cap. You do get the question of, is this a continuous tongue or is it segmented? And no reason why it can't be sometimes one, sometimes the other. But in terms of what would be deriving segmentation, were there segmentation, if you look out at the magnetopause, where you get a pulsed magnetic reconnection events, a series of pulses, the consequence of that down on Earth, if this is a fixed electron density profile, a contour of high electron density, the sun is up here, this is the reconnection line down in the ionosphere. If you only had motion of the plasma while there was reconnection going on and no motion at any other time, you would get a tongue of ionization with no segmentation. If, on the other hand, between the pulsed magnetic reconnection events, the region were migrating, if the merging gap were migrating first poleward and then relaxing back into the polar cap along with the plasma, then you end up getting segmentation or patches. And these are the flow lines of nothing has happened, now you're starting to get a reconnection event, now the reconnection potentials are taking place, you're getting circulation, you're pulling in high density sunlit plasma into the polar cap, it gets cut off, and you end up with this just sitting there waiting for the next reconnection event to start getting pushed farther in. And one of the big questions in the field is how often are you getting this segmentation? How often are you getting this pulsing? I just wanted to point out that in terms of what it would look like, if you had a continuous situation, which would be the stationary merging gap, that would all be filled in continuously. If, on the other hand, you've got a migrating merging gap, then you should be getting those patches. And when you go to the polar cap and look to see what do you actually get, most of the time what you get are these banana-shaped or oval-shaped regions of high-density plasma. Now, here I've just drawn contours of what the geometry would be for that plasma coming in. Here we're sitting on the ground and looking at optical emissions, and where you have a bright region, you have a lot of electrons recombining. Where you have a dark region, you have a very low background electron density. So this is telling you what you usually end up seeing in the central polar cap. In terms of if you look with an incoherent scatter radar instead, then what we're looking at here is a cut of about 10 degrees of latitude. This is the sunward side, the low latitude. This is the dark side in midwinter. This is the high latitude. So going from 70 degrees to 80 degrees of latitude. This is sunlit plasma. Then you have a gap. And then you've got these two guys here that are high density. Those, as it turns out, if you follow a series of these, are those patches that are working their way into the polar cap. Now here they've left. Here you have your next reconnection event, and this poleward boundary of high electron density leaps forward into the polar cap and fills in. If you are in a place where the background is dark, You can take images of this with imaging photometers, and then the imprint of when you open a flux tube, particles dump out of the feet of the flux tube, and you get an optical flash. And you get several other things going on, but this arc that you're seeing here was the previous patch that formed, and then what you are seeing here is the start of another poleward moving patch, which coincides with the leading edge from there to there to there. So what you're doing is tracking the poleward motion of the electron density profile. Those of you who have gotten into the literature already or will be getting into the literature, you'll be finding a lot of talking about flow shears. This is the incoherent scatter radar measurement of VI, the ion flow velocity, and the TI, the ion temperature. High velocity of the ions gives you frictional heating at high ion temperatures. So that could be either of the two. They look pretty much the same. Down here, we're now looking at the optical signature, and these are poleward moving from low latitude up to high latitude optical signatures, what the literature refers to as poleward moving forms. When they were first seen, people didn't know what was causing them, but they did know that they were moving poleward. Down here, we're looking now not with an incoherent scatter radar to measure temperatures and densities and velocities, and we're not looking at optical emissions to tell you where particles have dumped out of the feet of a field line, but you're looking at the super darn echoes. And when you get these high velocity shears, you get a lot of structuring that leads to these echoes. So you have several signatures that you can use to follow things. Now, so far, what I've been talking about, we all started on our journey here saying that we're going to look at plasma entering, crossing, and exiting the polar cap. So we've been focusing a lot on how the plasma is getting in. The next part is crossing the central polar cap. And here what we're doing is in the center of the polar cap, we're looking at optical emissions of high-density plasma is seen here as a bright spot. Here we're looking at an ionosonde, good old-fashioned instrument, showing an approaching echo because it's broken out by Doppler echo approaching and Doppler echo receding. So the two things to notice is while this high-density region is approaching you, you get an upshifted Doppler echo. After it's passed and over your shoulder, you're getting a receding echo. The other thing to notice is you don't have a simple single trace the way nice clean ionograms look at low latitudes. This is all filled in. It's what they refer to as spread F. And what that is telling you is that there's a lot of structure, a lot of irregularities in the electron density. And that is another thing that is characteristic of what's going on in these patches in the polar regions. And recall that we said we have two states of the polar cap. One state gives you these nice simple patches. The other state gives you the northward IMF signatures where you have optical emissions that run. This is the direction. The sun is in this direction, so it's sun-aligned, and lying on your back and looking up, if your eyes were sensitive enough to see these, you'd be able to tell what the time was just by seeing what the orientation of these lines are. They just stay fixed in the Earth-Sun coordinate system, pointing towards the sun as the Earth rotates under them. And if we were looking at the beginning at a full image of the entire polar cap from space, and you got the entire auroral oval with a nice theta aurora for IMF northward. When you're on the ground, you have to work a little harder, and you string several of these images together to piece together a picture. With an incoherent scatter radar to back you up, you can now measure temperatures, densities, flow velocities. the electrodynamics of those arcs they're simple Ohm's law arcs, where you have an electric field converging and a current is going up, which means electrons are coming in, and it's those incoming electrons that are giving you the impact excitation that gives you the optical emissions. But the reason for putting this view graph up is to call attention to the fact that are you looking at a velocity convergence, or are you looking at a velocity shear? And in fact, whether it's a shear or a convergence depends on your frame of reference. It's a question of what frame of reference have you chosen to go with. If you're sitting on one piece of plasma or sitting on the ground, you can choose, and therefore you can change a shear to a convergence or a convergence to a shear, but the currents that are up there are always in the rest frame of the neutrals. So you have no flexibility left once you start converting to the actual currents. And this is a pitch for saying that it's important to understand what the neutral winds are, what the neutral flow velocities are, and where you don't have them measured, then what your currents are telling you is somewhat in the eye of the beholder. In this particular case, we're collecting data at Sandrestrom, and we were able to make enough measurements that we could see that in the case of these arcs, we had a high ion temperature here with a very strong velocity shear. Here we had high electron temperatures, and you could decompose with a radar a lot of the electrical properties of that. In fact, with these new radars going in and the old radars out there, if you have good enough signal to noise ratio, you can literally calculate your Poynting flux, your Joule heating, the rate at which you're transferring energy from the ions to the neutrals, your particle energy deposition. So in terms of thinking about what you can start to do quantitatively, don't forget that this is not pie in the sky. This is things that we know how to do. So I've talked about how do patches get in, how do they cross the polar cap, patches and arcs. Now we're talking about how do they get out of the polar cap. And what we have here is a set of, we're now slicing time versus latitude, and we're just taking what people call kilograms. We're just looking through one slice per minute and just stacking 1 minute after another, and that allows you to see patches coming from the sunward direction, crossing overhead, and then going to the exit on the midnight side of the polar cap. So this patch would be up here, this patch would be down here, and the transit from there to here are where you see these streaks. One of the things that strikes you about this are these brightenings where the patch exit. We'll come back to that in a moment. But the other thing I want to call attention to is when these patches go across, the cartoons we usually draw make it all look as if all the patches come out right around midnight. When you put up a global string of measurements as the Earth rotates and you see where do these things actually come out, this is pretty much a Gaussian distribution of where they come out, and about 2/3 of the patches exit. These are 1 hour spaces, so about 2/3 of the patches exit within about 3 hours of midnight, but you've still got a lot of patches that are coming out closer to dawn and a lot of patches coming out closer to dusk. So they're really coming out the sides a lot more than is generally recognized, which is interesting in terms of following the history. In the old days, people used to do barium releases from rockets, and then they would just sort of watch plasma go across the sky. And in a way, you've got all the barium releases in the world that you could want just by following some of these patches. So we've talked about patches getting in, crossing, and getting out. We've talked about arcs are there for IMF north, patches for IMF south. Now let's do a little bit of talking about what's climate and what's weather. This is the IRI model, and this is the model of what the electron density is supposed to be doing, the peak density and H max at a high latitude station. And this is what's really observed as opposed to the model. And these are the patches that are coming out on the midnight side. So the point of this is to show that what comes in at noon comes out at midnight, and that's something that we have as reality, but some of the models do not yet have. And as a generality, there's many things that we'll be measuring with this polar station where the models that are based empirically on observations have an enormous amount to learn and improve from these new data sets that are coming out, because there are many regions of the world that previously have been data starved, and now we're going to have data to fill them in. I said at the beginning, in the middle, and I'll repeat once more that we have to be mindful that the polar cap is found in two states, IMF north and south. And if you had no measurements of satellites, no measurements of radars, no measurements other than you were just lying on your back with really super sensitive eyes, and when you saw this overhead, you knew that at the time that came into the polar cap, you had a southward IMF condition. If on the other hand, what you see is this, you knew that the conditions in the polar cap were dominated by a northward IMF. The other thing associated with that down here, what I've shown is the peak electron densities. And this electron density is the same as that electron density, but this is for the northward IMF condition, where you just don't get many high electron density cases. Here we're looking at the southward IMF, and starting off from a 3 megahertz base, you get a lot of peaks during the time that the patches are passing by. So in terms of the character, the optical signatures tell you a lot about whether it's north or south. The electron density peaks tell you a lot about what's north and south. The structuring of the plasma tells you a lot of what's north and south. And in terms of what's the physics, why is it highly structured? There's two plasma instabilities that people have been going to for decades to explain this. One of them is a shear-driven plasma instability, where the irregularities build on the side, on the edge of the shear. The other is a gradient drift instability, where the plasma structuring comes in on the tail. But, and for decades, people have all agreed that patches are structured by the gradient drift instability, and that arcs are structured by the shear-driven instability. But pause and think. We have been saying several times over that the way a patch gets into the polar cap is by virtue of a reconnection event, which involves a very strong plasma shear. So shouldn't we be getting a shear instability initially on the plasma in the patches before they get deeper into the polar cap? By making a measurement there and there, two closely spaced measurements, you can see how long it takes for plasma to structure. And the rise time for structuring for shears and gradient drift are very different. And what we learned by actually doing the measurement instead of reading the textbook is that patches really, as they first come into the polar cap, are dominated in their structure by the shear-driven instability. And then later, deeper in the polar cap, they're dominated by the gradient drift instability. Now, if you're on a satellite, how would you ever know whether patches were structured by shear or structured by gradient drift? Well, some lovely work done by Janti Basu and Rod Heelis, DE, other folks were involved, looking at comparing the electric field fluctuations and the electron density fluctuations. They found that the ratio of the fluctuations in electric field versus fluctuations in the electron density are different tenfold depending on how that plasma first got structured. So that's another tool that's out there that you can use. I've been getting a lot into structuring. In fact, it was structuring that first got us up into the polar cap, because what I'm looking at here now is an 11-year period, and this is the sunset number, or solar cycle, and these are the number of severe events of structure, scintillation, when the plasma gets structured over scale sizes of a fraction of a kilometer, 2 kilometers, you get strong fading of a radio signal. You end up losing your communications from satellites. You end up losing your navigation signals from satellites. And there's a lot of folks who have significant economic and other interests in making sure that that doesn't happen, which motivated getting a lot of people into the polar cap in the earlier years. And you'll sort of notice here that it's almost an on-off 6-year switch. For half of the solar cycle, you've got very severe scintillation. You wouldn't want to rely on navigation and communications too heavily during the sunspot max years. During sunspot minimum years, hey, you're fine. And also, here's winter, summer, winter, summer, winter, summer, marking the years, because when the summer is up, the conductivity shorts out those irregularity structures. During the winter, there's no E-region ionization to short out the structures, and they really get highly structured. There's also a diurnal cycle. The diurnal cycle where for about half of the day, every day, in universal time, you have strong structuring of these patches, and here you have very weak structuring of those patches. And in a moment we'll come to why that is. It's simple geometry. But in terms of when you do and don't have strong structuring, solar cycle, diurnal, and various other parameters that you can list. So let's go now from structuring plasma to the question of what's going on in the thermosphere while we have all of this circulation of the ions. There is transfer of momentum. There's frictional drag that in time will make the neutral velocities come up to speed with the ion velocities. And here we're looking at the ion velocities, here we're looking at the neutral velocities, and this is a nice climatological picture of what the thermospheric circulation system is if you turned on the IMF to be south and you had high electron densities and you just sort of let it sit there. It's sort of a climatological picture. And it turns out that there's a time constant you can derive from this relationship. What is the time it takes for the neutrals to come up to speed with the ions? And for 10 to the 6th per cubic centimeter, if you're on this side of the ocean, or 10 to the 12th per cubic meter if you're in Europe, or 9 megahertz if you're a radio ham, you get things coming up to speed in about half an hour. If your electron density were down from 9 megahertz to 3 megahertz, then, or the electron density were lower by a factor of 10, then this time constant is higher by a factor of 10. And in 5 hours, the Earth is rotated a quarter of a day. So for low electron densities, you just don't get this. For high electron densities, you do. And in terms of going up on a satellite, here we have an example of the ion velocities, and here are the neutral velocities, and they're pretty well aligned, so it's high electron density, and it's been going on for quite a while. So this is sort of the climatological example. Over here, the ion velocity is a lot different, a lot greater than the neutrals, and you'll notice that there's a very high ion temperature here. Now we'll go to weather, not to be confused with climate. Now what's happened is the IMF has just changed, the ion velocities have just changed, and that all happened so recently that the neutrals haven't yet had enough time to realize that they need to get back in lockstep with the ions. In this particular case, the electron densities are high, so it won't take them more than half an hour, but this switch just happened a couple of minutes ago, so now we've got huge ion temperature enhancements where the neutral velocities and the ion velocities are very different. And this sort of flopping back and forth of the IMF and the ion velocities going a lot faster than the neutrals is part of the weather issues that are up there all the time. Now, let's go to what can we measure with our new system. You recall I had mentioned that your patches, your high problems with the communication and navigation outages, your strong structuring, your large scintillation is half of the day it's on, half of the day it's off. And you can think of that in a very simple way. Here, you're looking from a satellite. This is the sunlit plasma. Here is your auroral oval. That is centered on the geomagnetic pole. And the sunlight is thinking in terms of the geographic pole. And over the course of 24 hours, the center of the geographic pole is wobbling around, and therefore this is wobbling that way and that way, that way and that way. And for roughly 12 hours in midwinter, this is nicely into the high electron density plasma, and you can get all the patches you want. For the other 12 hours a day, this is back here in low density plasma. The same physics is going on, the same transport is going on, the same circulation patterns, but what you're bringing in is low density plasma, and therefore no patches. So that's a 12-hour effect, and that's simple geometry. But now let's move on to what's new and exciting. This was the situation that we had. I should point out, if I haven't already, that 75 degrees is roughly where the cusp is, a magnetic latitude. That's where these patches are coming into the polar cap. That's where you have a lot of magnetic reconnection energy deposition, and that's right down here. So here you are in the central polar cap, and here you're kind of blind. Now, there's a huge advantage, because now you're able to follow plasma arcs steering northward, connecting up to the noon or midnight, or plasma entering down here and going clear across to the center of the polar cap. There's a whole new gallery of experiments that you could start to do, all the things I've been talking about, where we're putting together pieces from this day with pieces from that day, pieces from this instrument with pieces from that instrument, this theory and that theory. Now you've got it all there. You can watch it come in, watch it cross, watch it go out. You can see how long does it take to structure. You can answer a whole lot of questions, and this is just coming on. And remember what I showed you about measuring Poynting flux, particle energy deposition, energy transfer rate from ions to neutrals, all of those measurements that what I was showing you a little while ago are measured at Sonderstrom. That's what these radars do. So in terms of the physics, not only can you get new morphology that you've never had before, not only can you get new linkages as it comes in and as it crosses, and 12 hours later wash it as it goes out. But you can actually get real detailed physical parameters to watch what's going on. And on top of that, you've got these satellites up there, the new ones that are just coming online, and then our old faithful standbys that we've been relying on for decades are still going strong. We've got the Super Darn, which fills in a lot of the mesoscale flow velocities. We've got imagers that are transpolar from noon to midnight. And in terms of this data that I was showing you about where it's coming in from the sunward side, and then you have these poleward leaps where it connects to the midnight side of the auroral oval. Larry Lyons and his group have been doing some very fascinating work on the midnight side, following a lot of tracers, and a lot of the signatures are raising questions about where is the boundary between open and closed field lines? Do we have magnetic reconnection events going on the midnight side, just as we have on the day side? And there's a lot of experiments out there, a lot of data that's been tantalizingly suggesting that's the case. So this new combination of radars should be a gold mine for following that kind of thing. And not only the question of magnetic reconnection at midnight, but the question of magnetic reconnection on the day side. We still don't really know how much flux, magnetic flux, is coming into the polar cap. I was reading a Reviews of Geophysics article that was published 25 years ago, and one of the most pressing questions in the field was how much flux comes into the polar cap as a consequence of these transient reconnection events that make patches. We still don't know. But these new radars sure is our best chance of finally answering that one. And in terms of what is the consequence of those patches coming in, this again is that simple geometry I was talking about. And if you have a large BY, instead of the plasma sort of slowly going into the central polar cap, it goes sliding out to the left or sliding out to the right, depending on BY. And you're getting your strongest velocity flow shears for a large BY. Now, what kind of flow shears do we actually observe? We're all familiar with the Super Darn maps. We use them a great deal, both to plan our experiments, to see what's going on in real time, and post-analysis afterwards. Huge contribution to the field in terms of getting a global picture of what's going on. But to get that global picture, they have to do a lot of smoothing. And with that smoothing going on, you'll notice the highest velocity flow shown on this plot is about 1 kilometer a second. And when you do a lot of averaging of all the velocities, what you end up with is about 1 kilometer a second. So climate is average. You walk outside and you look to see what is the climate, say the temperature is going to be today. You never get a day when you walk outside that the temperature is what the climate says it would be. It's always hotter or colder, it's rainy or it's not. So let's talk about the weather. I was doing a lot of talking about flow shears. Well, here is a flow shear that's a 3 kilometer difference between the speed of the plasma here. That's a 200 kilometer or 2 degree latitude flow of plasma in the opposite direction to the background. Here's 1.5 kilometers a second in one direction, there in the opposite direction. So these are the kinds of things that we have not had an opportunity to really delve into a lot. Now, fine climate weather, does it matter? If we're following a patch of ionization from noon to midnight, and if it's going at 0.5 kilometer a second for a while and then 3 kilometers per second for a while, if on average the total time it takes to get from one point to another is the same, you get the same location for the plasma. But in terms of the energy transfer, the altitude profile of the heating rate, that is now getting into square law dependencies, nonlinear. So if you're going at a kilometer a second or less for half of the time and 2 kilometers a second for the other half, now you're putting in double the energy that you thought you were. If you're putting in 3 kilometers a second for half of the time, now you're putting in, you're getting an extra factor of 10 energy deposition. So yes, it does matter. And in fact, when you pursue this, it turns out that that was, when for 8 years we didn't know why the density doubled over the cusp, by just taking a look at simple fundamental physics and putting in not climate, but putting in weather, the answer fell right out. It was the ion frictional drag. Now, in terms of mathematical equivalence, there's a gorgeous paper by Thayer and Semeter in an appendix where they show the mathematical equivalence of, if you measure currents, you can do the calculation with currents. If you measure velocities, you can calculate with velocities. If you measure ion temperatures, you can measure with ion temperatures. So it's where you go to see, depending on what your measurement is. But if, in fact, what you want to do is causality instead of equivalence, there's a very nice paper by Strangeway that explains that if you want to look at causality, thanks, Rod, then what you want to do is look at the ion frictional drag term, because that's now getting not to mathematically equivalent, but to what is actually doing the driving of the physical process. And so it's this velocity squared, the square law dependence, that is going to start giving us a lot of effects that if we use climatology, we don't get it. If we use if we use weather, we do. And in terms of, well, how often does this happen? I was starting off showing it, the 3 kilometer a second flow shear with the superdarn. And here's with the incoherent scatter radars, here's with the DMSP. Doesn't matter what instrument you're going with, if you're making the measurement with a valid instrument, you get a spectral distribution of velocities. And in fact, if you look at the spectral distribution of velocities, sometimes it's 1, sometimes it's 2, sometimes it's 3 kilometers a second, square that. We're now looking at energy deposition rates of 1, 4, and 9. If you look at that distribution and then look at the density doublings that Lohr sees over the cusp, the two distributions are not that different in terms of the probability of occurrence. So in terms of climatological energy deposition rate versus the space weather energy deposition rate, these are the values for the climatology, but you're getting up to 2 to 9 times as great an energy deposition rate for the weather. Now, in terms of when does it matter, I've drawn a line here, because if you are getting down to where you have a huge, massive thermosphere, its response time is very long. We all know that the thermosphere can't respond in less than a lot of hours to a lot of heat input. What we rarely stop and think about is, even though it takes a lot of hours down here, as we go up in altitude, the atmosphere gets more tenuous. The neutral densities get a lot smaller, and therefore the response time gets a lot shorter. And the response time depends in part on that velocity squared term, or the energy deposition rate. And it turns out once you're above 200 kilometers, the response time of the thermosphere is a fraction of an hour. When you're down where we're usually thinking about the energy, where most of the energy does go, you're talking about many hours. And so, well, what can, if you give me 15 minutes of 10 times the energy deposition rate above 200 kilometers, what can I give you back for that? So instead of using my isopicnic point at 120 kilometers or wherever your model says nothing changes, let me just take my isopicnic point at 200 kilometers and say I didn't have enough time to change the temperature down there, but I sure had enough time to change the temperature here. If I put in the kinds of velocities that we're seeing, I can get a 10% change here, but then if I follow that exponential change, I can get 100% change of neutral density up here. So that's part of the input response. Now, Richmond did a gorgeous publication of Poynting's theorem, and when you have satellites and nothing else, you've got to go to the measurements of the Poynting flux. But in terms of, that's telling you the energy coming in coming into the top. But now, where does that energy go? That's the other half of the question. What is the response? If all the energy goes down here, you're not going to do anything. If all the energy went in here, you'd get a huge response. I mean, that's the simple-minded way of looking at it in terms of mass. Now, what Richmond did was a thorough mathematical treatment, and he, based on his treatment, very nice paper, he comes to the conclusion that the Poynting flux, if in fact you're in a region of high Peterson conductance, you can significantly underestimate the impact of the Poynting flux. If you're in regions of low conductance, you can significantly overestimate the impact. And that is another way of saying the very same thing that I was just saying here, but mathematically rigorous. I'd like to make an appeal as well for the measurement of neutral densities, neutral winds. Jan Soike did a very nice modeling study with years worth of data that Van Eycken arranged to be done at ISCAT. And the short of it, I'm not going to read the abstract to you, but the short of it is with the neutral wind models that are out there, you're better off assuming that there's no wind in terms of getting the right answer than to put in what comes out of any of the models. So we need to do a much better job on the neutral winds. Now, at the time Al Hadin put that together, it was the best information we had. It was a great contribution, but we need a lot more information on neutrals. This is the measurement I was referring to where we determined that patches first are structured by shear and later in the polar cap by gradient drift. You just get two receivers not very far from the cusp, measure the structure here, measure the structure there, see how much time it takes to structure how much more. Very straightforward experiment. Here's another interesting result in terms of ion flows. It turns out that what we're looking at here is the location of the cusp. We're looking with a meridian scanning photometer, and here the cusp is poleward, then it passes overhead, then it goes back poleward, and then it comes back and passes overhead. When you are under the cusp, you get high ion temperatures, high velocities, high TEs. You get huge ion upflows. When you're looking in the wrong place, you're going to find your watch. When you're looking where there's nothing going on, you don't see those high upflows. So you want to be making sure that your radar is reaching out to where the action is instead of just looking straight up B. But in terms of these velocity shears, these reconnection events, for sure you're going to get strong ion upflows there. That is part of the answer. In terms of key questions, and now I'm in the final few slides, one of the key questions for this group is how does the solar wind magnetosphere ionosphere coupling affect the composition and structure of the ionosphere in terms of the view graphs that I showed in the last hour, pointing out that you've got two different states and you can recognize what state you're in from the ground as well as from satellites and you can make some remarkably detailed quantitative measurements that will tell you about the thermal balance, the energy balance, and the electrodynamics of what's going on in those events. In terms of another question that we're talking about, what are the effects on the neutral atmosphere? I spent a bit of time talking about going back to the basic equations, of which one is basically getting into the causal, the ion-neutral energy transfer, but the mathematical equivalence depending on what you're measuring. And this is using measurements from the radar input. You can get models that show big density changes at the higher altitudes. What governs the internal structure and RF propagation just pointed out that there's this big difference in the structure if you measure both the fluctuations in electric field and fluctuations in electron density. You can separate what came from a shear from what came from a gradient drift. And by putting a pair of receivers at two different distances downstream from where the event starts, you can just see how long it takes for the instability to set in. In terms of how do these processes I'm going to cheat. How do these processes affect plasma outflow and its impact on magnetosphere configuration? Well, magnetic reconnection events, especially if it involves soft particles, not hard particles, you're going to get big ion outflows. And that applies with your new radar, not only to the cusp by day, but if you have large soft particle events dumping in at midnight, 12 hours later, you ought to have these ion upflows then as well. I haven't seen them reported in literature, but wherever you have a strong soft particle flux, they just have to be there from the physics, so someone will get around to looking to see if that's true. And then last, I just couldn't resist throwing in what is the role of pulsed magnetic reconnection in unifying our base of understanding at the crossroads of all of these questions that we're looking at and the crossroads of all of these instruments. And this is simply a reminder. It's just one example of what that radar in this observing mode would see a velocity shear getting up 2 kilometers a second, starting off at maybe 50 kilometers wide, ending up at hundreds of kilometers wide, and then the IMF flips and it stops. And then you get the IMF coming back again. This is a guy where the BY component lasted for just 5 minutes. It's reconnection on the lobe cell. And this little blue stripe here lasts for 5 minutes, and it starts in sync with the time that the BY flipped. So there's a lot of data that, with the satellites and with the ground-based instruments, is just sort of, it's a gold mine. I'm excited for you guys who are getting in just at this time.